So in this question, we're looking at let k be a positive integer and 1 to the power k plus 2 to the power k plus going up to n to the power k is BigO of n to the power of k plus 1. Okay, so what's the definition of BigO? So if I claim that let there be a function f of x, and f of x is BigO of g of x, then this statement is true if there exists some constant c times g of x that happens to be an upper bound on f of x for some k as long as x happens to be greater than that k. So here is the definition. This is the definition of BigO, and this is the expression. So this is the expression that involves BigO, and here is the definition where I have only the mathematical operators that give the semantics of BigO in this first one. Now the question over here is this function over here BigO of n to the power of k plus 1. Now what that means is that if I write everything on the left hand side, which is 1 to the power k plus 2 to the power k, going everything up to n to the power k. Okay, I need to figure out, is there some function over here which is less than or equal to g of x, which is n to the power k plus 1 times c. Can I figure out some c for which this inequality will be true, and there is some n for which is going to be greater than some c. So if I can figure out this c and figure out this constant c, then I do know that n to the power k plus 1 is BigO of this expression over here. So let's think about this. If I rewrite 1 to the power k plus 2 to the power k, everything up to n to the power k, and I replace this 1 with an n. So wherever I see that 1 there, I'm going to replace that with an n. Where I see a 2, I replace that with an n. And when I see an n, well, I'm going to leave it as it is, n. So what I'm doing is I'm replacing all these constants, 1, 2, 3, 4, all the bases, with n over here, which means that this is n to the power k. If I replace 1 with an n, I replace 2 with an n, so that becomes n as well, plus n to the power k. Now everything in yellow is definitely going to be greater or equal to everything in orange. And you can see that the first step that I've done here is I have started working with my expression in orange. I've introduced an inequality operator. And I've got this entire expression in yellow that happens to be greater or equal to this piece in orange. Okay, can I simplify this expression in yellow here? Well, this expression in yellow, how many actual terms do I have there? Well, I've got n terms. So this piece over here is my term 1, this piece over here is my term 2, and this piece over here is my term n. So I've got n of these terms. Okay, so I've got n times n to the power k. If I just add them up, I've got n of these terms, and each term happens to be n to the power k, which is greater or equal to 1 to the power k plus 2 to the power k plus all the way up to n to the power k. Now what is n times n to the power k? Well, this is going to be n to the power of k plus 1. So this is 2 to the power k, everything up to n to the power k. That's my left hand side, which is less than or equal to n to the power of k plus 1. Okay, now coming back to this expression in pink here. What's that c? What is that value of c? And what is that value of z that I can ensure will be true for what I've got over here in blue? Okay, so my c over here is 1. When I make c equals to 1, I'm going to make my z equal to 1. This will ensure the 1 to the power k plus 2 to the power k going all the way up to n to the power k will be less than or equal to n to the power of k plus 1. Okay, so by using from this mathematical definition, I can now jump into, if I want to get rid of the inequality, I can simply say 1 to the power k plus 2 to the power k all the way up to n to the power k is BigO of n to the power of k plus 1. So from here, I come back over here, and this piece is consistent with the question that I started with.